Hello, everybody. So what we're going to be looking at today is section 3.3, arc length and curvature. Now, I think this is a pretty easy topic. The last one was too. The last couple have been easy, I think. I feel like what we've been doing lately is not so bad. Um, and arc length is a topic that you should already be familiar with to some extent. Most Calculus 2 classes cover arc length, right? So in Calc 2, you should have seen this, or Calc 1. I don't know, Calc 1 or Calc 2. So in Calculus 1 or 2, you should have seen arc length, right? Which is just the length of a piece of a curve. Okay. And you could have seen it written several different ways. So it could have been this way, might have been shown to you several different ways. So if your curve is defined by like y equals f of t, then your integral could be like an integral from a to b of, it was like a square root 1 plus f prime of t dt. No, sorry, I want to use x. Sorry, x dx, like that. If your curve was x is a function of y, which you could have, that was not an issue. It would be a different a and a b, but then a square root 1 plus g prime of y, and then a dy integral. And if your curve was parametric, where you had x, let's say, is a function of t, and y, that's a y, is also a function of t, then your integral would have been an integral from a to b of square root, and it would have been f prime of t plus, oh, I don't know what I'm doing. I wrote these all wrong. They're all squared. Brain not working. F prime squared plus g prime squared dt. Okay, so you would have seen this in several different contexts. And it's still the same in this class, okay? So like what you learned about arc length basically still applies. So for us, arc length in space, I'll call it, it's going to be the same thing. So what you've got is, what do we have? So let, okay. So let r of t be a curve. So we got f of t, I, g of t, j, h of t, k. Right? Then what we'll say is that the length of the arc, the portion of the curve, in t between some starting t value and some ending t value. So what we're considering is in space, you've got a curve, but we got some starting point and some ending point, t1, t2, doesn't matter which one's on which side, but we have a little piece of the curve that way. So the length of the portion of the curve in that region is given by S equals, and it's basically just going to be this definition of the parametric curves again, just with 3 functions instead of 2. So we'll have an integral from t1 to t2 instead of a and b. And it will be square root, and it's going to be, where is it? F of t squared, f prime of t, sorry, squared, plus g prime of t squared, plus h prime of t squared, and then dt. That's it. Um, so it's really just the same as what we've done before. And that's the formula for arc length. Another way to write it, by the way, is going to be, this might look familiar to you. It also looks like the magnitude of a vector, right? This looks like a magnitude, right? So you could also write it this way. So you could also write it this way. S equals integral of t1 to t2, and the magnitude of the vector, it's f prime g prime h prime, so that's the derivative of r. So you could actually write it very concisely as the magnitude of r prime dt. So that's just shorter to write, right? That's all. That's the only reason behind it. Okay, so that's how you do it. And the main thing here is that it's still difficult to do because a lot of these integrals are difficult or impossible because of the square root. So note that the square root makes these integrals possibly difficult. So they could be challenging or even impossible to solve by hand. Okay, but we can still write them out. So let's do one. Just going to pull an example up here. We're going to example, find length of r of t equals, oh, they're killing me here. Okay, we're gonna do, let me think about this. Sorry. Yeah, we can do it. Okay. 3 sine t I plus 3 cosine t j plus 4t k. And we need a region too. So find the length of that for t between two t values. And let's just go, let's go 0 to 2 pi. Okay. And you might remember that what this kind of shape is, right? Where you've got like a sine, a cosine, and then a constant times t. You get the sine and the cosine make circles, and this just increases. So what you get is a helix. This isn't the standard one because the sine and the cosine are reversed from normal. So if you put in a 0 here, what you actually get is 0, comma 3. So you actually give a 3 on the y-axis instead of the x-axis. And then as that increases to pi over 2, then you end up over here. So it looks like something like this. Okay. And drawing it stopping right there because, oh, actually, I shouldn't have. I should have drawn this only up to, well, we'll do, here's what we'll do. We'll change this to 4 pi. And I'm doing 4 pi because with these particular equations, 4 pi is actually going to give me 2 revolutions around the circle. So I was drawing the right amount there. All right, so that's our curve. So we want to know the length of that curve. And so what you do is you just, find r prime. You need the derivative vector. but that's easy a lot of times. Um, so derivative, I'm going to write it also in my preferred notation. So the derivative of 3 sine t is, of course, 3 cosine t. The derivative of 3 cosine t is going to be negative 3 sine t. And then your derivative of 4t is going to be 4, right? So you do that first. And then you know that your, there's different ways to write it, but your arc length integral is then s equals integral. Our limits of integration are given. They're 0 and 4 pi. And this is going to be the magnitude of this r prime vector, dt. And that's why it's nice to remember this notation, just because this is easy to remember, and then you can think about the square roots afterwards. So this is going to be the integral from 0 to 4 pi square root, and then it's this squared, this squared, this squared. So you have 3 cosine t squared plus negative 3 sine t squared plus 4 squared dt. So far, so good. 0 to 4 pi. So you work this out. We got 9 cosine squared t plus 9 sine squared t plus 16 dt. Oh, wow, I didn't even know the numbers were going to work out, but they're nice. We saw this in the previous lecture, right? Remember that, sine squared theta plus cosine squared theta, of course, is 1, right? If you just put like numbers in front, like 7 sine squared theta plus 7 cosine squared theta, of course, that's just going to be 7, right? Because we're just multiplying everything by 7. So when you see the part that I've underlined here, that should just be 9 using that identity. So you use your identity there, and we have the integral from 0 to 4 pi square root. That's all just 9 and then plus that 16. So that's really convenient, right? Because you just add those together, you just have square root 25 dt, which of course is the integral from 0 to 4 pi of simply 5 dt, which is, of course, the antiderivative of 5 is 5t from 0 to 4 pi, and you plug in your limit, so you have 5 times 4 pi minus 5 times 0, and you get 20 pi for that length of the curve. So the length of the curve is 20 pi. So that's how it goes when everything is nice. Of course, a lot of these integrals are not necessarily going to be nice. You just get what you get. So that. What else? Okay, yeah. So there's more stuff to do here. So that's why I'm kind of going through the basic arc length a little bit quickly here. So how do I want to say this here? Okay. Consider, so this is going to be arc length parameterizations, which takes us a little bit to get to, but parameterizations. Okay, so where do we start there? So here's the idea. So suppose we're still looking at an arc length integral, but instead of the normal one, so instead of like an integral like this, s equals t1 to t2 of, I'm just going to say, hold on here. Yeah, okay, I'll have to write it out. F prime squared plus g prime squared plus h prime squared dt, we want to consider this one. So it looks the same, so I'm duplicating it, except what we're going to do is we're going to change this bottom one to a constant a. We're going to change the top one to a variable. I'm going to call it t. And if I put the top, if the top one is t here, then I shouldn't be using t here. So I got to change all those. Maybe I should have just rewrote the whole thing. I don't know, but we're going to change them all. So u, du. Okay. And then that makes this a function of t. It's a function of t, right? Because when you're done doing this integral, you're going to plug in the t and the a. So t is going to be the only variable left. A is going to be a constant for us. Okay, so it's almost the same integral, but it's a little bit different. Okay, and what this s of t is we're going to call that the arc length function. This is going to be a function of t. This is a function of t, and I'm going to call it the arc length function. Okay. The reason it's called the arc length function is because if a is going to be like 0, for example, so we call it this because if a is I'll say 0, but it could be anything. So if a equals 0, for example, then s of I'm just going to put a number here. So like s of 7 would be the arc length of the curve, right? The curve was r of t over, and then the interval would be 0 and 7, right? For example. So you have to kind of, adjust these, right? I used a 0 and I used a 7. So this was a 0 and this was a 7. Okay. And we call it the arc length function, right? Because you evaluate s and it tells you the arc length. So there's that. Okay. Now, we don't really do much with it. You might have a problem that says calculate the arc length function, and then they just want you to do this integral. That's fine. But there are certain properties of this, which is going to be this. So here's a property. So if r of t is a smooth curve, so smooth means differentiable here, smooth curve, then how do I want to say it? No, I want to say if r of t is a smooth curve, then the magnitude of r prime of t equals 1 for all t, then s of t is the integral from a to t of the magnitude of r of u. That's just our definition of arc length integral. Sorry, it should have been a du. And that's going to be the integral from a to t of 1 du. So remember here, so the arc length integral had this magnitude of r prime, right? Like we saw that in our example, right? Magnitude of r prime. Now, what we said here was we just had a magic r prime where the magnitude was always 1. So if the magnitude is always 1, then the magnitude is 1. So we just replaced it with 1. And so this is really considering a very specific case where the magnitude is 1. But if the magnitude is 1, then you get this integral. And if you get this integral, when you do it, you're just going to get t minus a for the answer. First you get a u, and then you plug in the t and the a, and you get t minus a. What's the point? The point is that the parameter was the arc length, right? Because s of t is just t, basically. Like if a is 0, then it's just t. Yeah, okay, then that equals that. And if a equals 0, then s of t would just be t. And what that's saying is, so for example, the point is that the answer to a question like this, what is the arc length of the curve over, and I say, like, if I say from 0 less than t less than, I'm just going to put a number here, so like 33, has the answer, arc length is 33. Right. Now, obviously, that's a weird situation, right? That doesn't just happen, right? Like, what's the arc length from 0 to 33? 33. That doesn't usually happen. Like in our example, like we did the arc length from 0, we did the arc length from 0 to 4 pi. And our answer was 20 pi, right? Not 4 pi. So that's not the usual case. So I'm describing a weird situation here, right? So I'm saying, property, if r of t is a smooth curve and this magnitude is 1 for all t, then this stuff happens, okay? So it's like a weird situation. It doesn't always happen. It's like a special case, okay? Now, if that does happen, then we give it a name here. So let's see here. Here's the definition of this stuff. Let R be a smooth curve for t greater than a, then the arc length function, we already defined this, but I have some other stuff to say. So the arc length function is given by s of t equals integral from a to t, magnitude r prime of u du, like that. And then they say, furthermore, the derivative of s with respect to t yeah, that's actually right. Okay, so the derivative of s, which I didn't do yet, but if you take the derivative of this function, what you get is the magnitude of r prime of t, which is going to be positive. It's going to be positive because the arc length, like the arc length from 0 to 2 is bigger than the arc length from 0 to 1, for example, right? There's more curve from 0 to 2 than there is from 0 to 1. And the arc length is always a positive number. So you can't have a negative arc length, for example. So, they're just saying this. So the derivative of this, sorry, having trouble here, computer's issues. The derivative of s, which is ds dt, would be the derivative of this, which is this by the, what's it called? The fundamental theorem of calculus. And that will just be positive. And then they go on to say, if the magnitude of r prime of t equals 1 for t greater than or equal to a, And then this is what we've already done so far, but I'm going to give it this name here. Then the parameter t represents the arc length from starting point t equals a. Okay, so that's basically just a summary of what we just did, right? Like when I said, what's the arc length from 0 to 33? Answer 33. Um, that's what this is saying too. Okay, so they just put it together here. Now, there's a, they don't have it as a theorem. They don't. Okay. Um, so there's a thing you can do called um, finding the arc length parameterization. So they make you do this. Oops. All right, finding the arc length parameterization. So they want, like, this is for the case where you don't have what they're talking about in the previous definition, but you want it. Okay, so finding the arc length parameterization. So this is, you know, this means you don't have what we just talked about, but you want to have it. Okay, so what do you do? So there's kind of steps to do this. So what you want to do is find the S of t. So step one, find the arc length function, S of t. All right. Now, when you find the arc length function of S of t, it's going to be a function of t, right? So it could be anything. So like, just imagine it's like S of t equals like 3t plus 2, right? Just a function. Okay. That's just an example. Then what you would do is you might be able to solve that for t. Can't always, but you might be able to solve it for t. Right? So like as the example again, if we had s, right? So I'm just going to stop writing of t. If you had s equals 3t plus 2, of course you can move the 2 over like that, and then you can divide by 3. Something like that. You might be able to solve it for t. So that's an example. And if you can solve it for t, then what you do is you take that, you do solve it for t, and go back to the original parameterization. The original parameter t with the new parameter s, using according to the relationship, the algebraic relationship. Okay, you don't just change all the t's to s's. And then the result there, the result is has the property, the parameter is the arc length. Okay. Now, remember, what does parameter s what does parameter is the arc length mean? It means this kind of thing. That's what we're talking about. Okay, so you can make that happen if you really want it to happen. Okay, so let me see if I can find one. Maybe there's one open. No, that's curvature. Okay. Um, Sorry, just scrolling here looking for one. One turn of the helix, arc length, integral, set of integral, circumference. Find the length. The what? Well, that's really frustrating. Okay, well, I can only find their example, so I guess we'll do it. Um, so let's do, where is one? Okay. Find the arc length parameterization of R of t equals uh, t plus 3, 2t minus 4, 2t, and that's t greater than or equal to 3. Okay, so here's what we're going to do, right? So we have to do this. So step one is what I set up here. We need to find the arc length function s of t. Find s of t. So that's the arc length function. So that was the one that looks like a to t, and then it was magnitude r prime u du. Okay, so we got to do that. So we have the a. This is actually the a, right? That's why they told you this. So your lower limit is given there, 3. Your top limit is t because we want it to have the t in there. It's a variable that we're going to have in our answer. And then you've got the r prime of u, magnitude of r prime of u. So you take the, we need the derivative of this function here. Now the derivative is going to be in terms of t, right? Normally. So like, oops. Normally the derivative is going to be in terms of t. So like r prime of t is the derivative here. So what's the derivative of t plus 3? 1. What's the derivative of 2t minus 4? 2. What's the derivative of 2t? 2, right? Now, if there were any t's, you would have to change them to u to get r prime of u. Now, there aren't any, so we don't do anything. But this is technically, you change t's to u's for, the integral. Right? Because it's got a u. Now, there aren't any to change, so we don't have to do that here, but in general, you do. So 1, 2, 2. So you do that. We work this integral out. So 3 to t, magnitude of this vector. So the magnitude of the vector is simply going to be 1 squared, 2 squared, 2 squared du. So we got, what do we got? 4 and 4 and 1. So it's square root 9 du. That's nice. So it's just going to be 3. So this is going to be 3 u from 3 to t, right? When we do the antiderivative. So 3t minus 3 times 3. So you end up with 3t minus 9, right? So that's your integral. But your integral is a function of t. Okay, so that's your arc length function. Oops, not what I wanted. Arc length function is what we just calculated. Okay, So then step 2 was you might be able to solve that for t. So try to solve that for t. So we just go s equals 3t minus 9. And so you don't really write the change, just write s and not s of t. Okay. So try to solve that for t. That's just regular algebra. So like add the 9 to both sides, divide both sides by 3. So you end up with t equals s over 3 plus 3, right? So you do that. Okay. Now, actually, says solve for t. We did that. Replace the original parameter t with the new parameter s. That's in the parameterization of the curve. So step 3 is going to be the original curve is r of t was t plus 3, comma 2t minus 4, comma 2t, and that was for t greater than or equal to 3. Okay, now our new curve, we're going to replace the t's with s's. Using what we just had, which is s plus 3, s over 3 plus 3 equals t. So now this is going to be r of s, actually, which is going to be t, which is s over 3 plus 3 plus 3, comma, and then you put this in for the second one. So you have 2 s over 3 plus 3 minus 4, and then 2 s over 3 plus 3. Simplify that if you can. So you have s over 3 plus 6. The other one is going to be 2s over 3, and then 2s over 3, but then 2 times 3 is 6. 6 minus 4 is 2. So like that. And the last one here, 2s over 3 again, and then plus 6. So this is r of s. Okay. And you can find the, you can even deal with the t greater than or equal to 3 thing. Because if you put in the t, which is s over 3 plus 3, you have s over 3 plus 3 greater than or equal to 3. Subtract 3 from both sides, you have s over 3 greater than 3. Then you have greater than 0. And then you have s greater than 0. It's always going to be s greater than 0. Okay, so that's the answer, right? So this is the answer. So this is the curve parameterized by arc length. Okay, now why do we care? The reason you would care is because you'd be able to answer this way. So for example, what is the arc length? For the portion of the curve in some interval. So the portion of the curve in, let's just say like s between 0 and 12, for example. What is the arc length in there? Answer 12. Right? That's the point of having the curve parameterized by arc length. If somebody asks you what's the arc length between 0 and 12, you just say 12. Easy peasy. And that's the whole point of doing that. When you're doing problems in the book, right, or the homework, they ask for this, but they don't have you do anything with it. That's why we did it, and then I just kind of tacked this on the end. That's the point of having a curve parameterized by arc length. Okay, last topic, promise. Oh, we're 40 minutes in. That's not bad. Okay, so you have a small amount of these on the homework. I think I took out most of it, okay? Because I didn't really want you to have to do curvature here, but we have a little. Okay, so so graphs, have some curvature, or curves have some curvature. Curvature, right? Like if I draw one like this, right? Then over here it's a relatively wide curve, and over here it's a relatively skinny curve. And so you can represent that curvature by a circle. Like if I draw a circle on here like this, then there's a circle of a certain size that will match the curvature. Okay. And then if I draw a circle over here, that's not a circle. If I draw a circle over here, if I draw a circle over here, then it would be a smaller circle that actually matched the curvature, right? So that's how we represent a curvature, or that's the idea here. Okay. Um, so you can think about the size as related to that. So you could think of different places on the graph as having a radius of curvature, right? Which is it curves as much as a circle that you can put right there has. Okay, so that's the idea. So you can have a bigger radius or smaller radius. So gentle curves have a big radius. Radius slash curvature, and tighter curves have smaller radius. Big radius, I should say, small curvature. Okay. Yeah. All right. So big radius means small curvature, and smaller radius means big curvature. Okay. Anyway, but we define curvature mathematically this way. So definition for us, let C be a smooth curve. R of S, where S is the arc length parameter. So that's why you need to be able to do the arc length parameter. Although I believe that the homework that you guys have should all be parameterized by the arc length parameter. So like I don't think you have to do that yourself on these. Just looking at them real quick, I think that's the case. Okay, so let C be a smooth curve where R of S, where S is the arc length parameter. I don't know why I put vector over that. We define the curvature. They use a kappa, it looks like, at S is given by kappa equals the magnitude of dt over ds or t prime of s. Okay, great. What is the what's the t though, right? So you have to remember that where remember t of t. I'll write it in terms of s actually. T of s vector vector. The way you get that is it's like r of s over magnitude r of s, right? It needed to be unit. It needed to be a unit vector. So it's the sorry unit tangent vector. Okay, so that's your definition of curvature. Okay, um, so it's going to be a measure of how curved the function is at a particular point. So it measures um, how big the curvature of the curve C is at a point. All right. And so that's what it is. So, it's a little um, I don't know, it's a thing. So we can calculate it and let's see. I'm a little bit confused here. What did I just write? Okay, I wrote the thing I did want to write. So we're going to do some calculations with this, but also we can say this. So this is an alternate formulation. So if C is smooth, given by R of t, right? So that's not arc length parameter anymore. Then what you'd have to do is the kappa would be magnitude of t, not double prime, t prime of t over r prime of t, like that. And so the difference between this, if you look, is that this is t prime of s, and there's no denominator. This is t prime of s, and there is a denominator because the parameter wasn't the arc length, so you like this is needed to adjust for it, right? So this is what's different. Okay, now if C is a curve in 3D, then you could use kind of this formula, magnitude of R prime cross R double prime, which we haven't even really spent any time calculating, magnitude R prime of T cubed. Okay. And if C is the 2D plot, y equals f of x, right? Like you would get in calculus 1 class, and y prime and y double prime exist, then the curvature is the absolute value of y double prime over 1 plus y prime squared to the 3 halves. Okay, we are not, I'm not going to prove those. So we're not going to prove these. We're just going to state those, and you can use whichever one you want if they come up, which I don't think they will. So yeah. So let us do a problem. Okay. Example. Find the curvature. Actually, let's do one on your homework. Okay. So find the curvature of r of s. We got cosine 9s over 9i plus sine 9s over 9j. And they say where s is the arc length parameter. So that means you can use the first formula. All right. So that's the first step, right? Identify the formula. So since s is the arc length parameter, our formula is what? Kappa is what? So you scroll up here, it is bum 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 t prime of s. But we got to calculate t of s. And then we can do t prime of s. Okay? So yeah. All right. So step one is, which I guess I'm actually calling step two. So first we need to find t, which is r prime of s over the magnitude of r prime of s, right? So that's what we need to find. So what's r? R is given. Where is it? Here it is. Oh, I can't. Thought I was going to be able to make that. Thought I was going to be able to make that smaller. Okay. So there's r of s. So we need r prime, right? So that means that r prime of s, we need the derivative of this. Now that's not going to be hard. The derivative of this derivative of the cosine function is negative sine. So you get negative sine 9s. Chain rule says multiply by 9. Then for the derivative of sine 9s, it's going to be cosine 9s. Chain rule says multiply by 9 for 9j. So we simply get negative sine 9s I plus cosine 9s j. So we have that. Then we need to divide that by its own magnitude. So we have t of s is r prime over magnitude r prime. So I'm going to put it in this notation, negative sine 9s cosine 9s over magnitude sine 9s negative cosine 9s. So then we get negative sine 9s. It's a negative sign, not negative 9. I don't talking about anymore. Square root. And I'm just going to write it. It's going to be sine squared 9s plus cosine squared 9s. Right? Because we're squaring it. So then you get negative sine 9s, comma, cosine 9s over square root. Now this is a cosine plus a sine, which means it's just 1. So your answer here is negative sine 9s cosine 9s. And that is t of s. Okay, so we got that. Now that's not the answer to the problem. That's only the answer for the first part. So there we go. So what do we need now? After we find the t, oops, we're going to need this formula, which is the magnitude of t prime. So the formula for curvature is this. Kappa magnitude t prime. So this is the derivative. We need to find the derivative. So we're going to have kappa magnitude. We need to do another derivative of this function. Okay, so we take the derivative. So what's the derivative of negative sine 9s? It's going to be negative cosine 9s times 9. So it's going to be negative 9 cosine 9s. And then the other one is going to be 9 sine 9s. So we take those derivatives, okay? Then we need to do the magnitude of this vector. So it's going to be negative 9 cosine 9s squared plus 9 sine 9s squared, which is going to be square root 81 cosine squared 9s plus 81 sine squared 9s, which is going to be square root 81, which is going to be 9. So they say the curvature is kappa equals 9. And it's a constant, by the way. Normally it's a function, right? It could be a function. A function of s. But we had, our curve was a circle. So curvature is just constant everywhere. So the curvature is just the same. Okay. So that's how you calculate a curvature. I think you have to do it a couple times in the homework. It's not particularly hard. It's just kind of, long, too long, but you can calculate it, take it step by step. You just have to keep track of like what's what, right? Like you see kappa equals t prime, and then that's steps to get that, right? That's the tangent normal, the unit tangent vector. So you have to like the derivative of the unit tangent. So first you have to find the derivative, divide it by its magnitude to get the unit tangent. After you get the unit tangent, then you can take the derivative of the unit tangent and then find its magnitude to get curvature. So like curvature is related to the second derivative. Like you probably remember that from like concavity, like concave up, concave down. Had to do with the second derivative. So it's the same thing here, right? Because like kappa is the magnitude of the derivative of the tangent, but the tangent was the derivative of the curve, basically. So this is the second derivative of the curve with some other stuff thrown in to like make the magnitude 1, right? The unit tangent. Yeah. Okay. So anyway, you can calculate it though. It's just a little bit of work. Anyway, that is that for this lecture. So I will see you guys at some point in the future, probably tomorrow. Have a good day, weekend, whatever it is.